RF Man here. Today we're going to talk about how to design and build a low-pass filter. This video will be in two parts. Part one will show how we design it using off-the-shelf software. And part two will show how we build a filter and we test it on the spectrum analyzer. So typically you'd have a low-pass filter for each band that you transmit on. And general arrangement would be a number of low-pass filters on one PC board with relays to switch them in and out, and then a selector switch to select your band. For this video, I'm going to just concentrate on building a low-pass filter for the 10, 11, and 12 meter band. So that'll basically range from 24.8 all the way up to 29.7 megahertz. So this is the software that I use. It's a free download. If I go ahead and close this and open up my browser, okay, this is the website. Let me see if I can zoom. You see there, tonesoftware.com. Okay, and this is the LC software. L is in inductor and C is in capacitor. And there's the download button. You download it onto your PC and use it. It's freeware, and the results correlate with most of the other calculators on the website and most of the calculations that I've done using my Excel spreadsheets. So it's a good tool, good designer tool, and it makes the job easy. So there's the icon up there. You see the LC. I'm just going to load the software, and it's very simple to use. First thing we do is we click on New Design, and here's all the parameters that we need to design a filter. This will give you not only the schematic but also the plot showing you the roll-off. So typically for a low-pass filter, an LPF, we have an inductor on the input and an inductor on the output. So let me just shift over here to my other bench. Get a look at my lab here. Once my camera focuses, there you go. And this is what the low-pass filter looks like when it's assembled. So in part two, we're actually going to talk about where to source the parts and how to build the filter, and then how to test the filter on a spectrum analyzer. But that's what it looks like. And you do a quick count there, you see 5 components. Okay, so this filter has 5 poles, typically referred to as a 5th order filter. Okay, so an LC filter that has 2 poles, typically an L network, would basically be a 2nd order filter. Okay, this particular filter here that has 5 components is a 5th order filter. If you design one with 7 components, that's a 7 order filter. So why have 5 poles and not 7 poles? Well, it depends what the roll-off is and what you really need in order to attenuate the harmonics in the bands that you're transmitting on. And typically a 5th order filter gives you a good roll-off. A 7th order filter gives you even a sharper roll-off. Okay, so we'll be able to look at that once we design this. So low-pass filter, we said we're going to go with this type here, which is an inductor on the input. Okay, then there's a number of different filter families. You can use Butterworth or Chevy-Chev. I like the Chevy-Chev filter because the roll-off is steeper, so it responds much sharper. And you'll probably see on the internet there's a lot of low-pass filters that use the Chevy-Chev model, so we're going to select that. Of course, you can compare the two very easily if you like. Okay, and then we're looking at the center frequency. So we said we're going to design a filter from 12 to 10 megahertz, 10 meters rather, and On the upper side of the 10 meter band, that gives us 29.7 megahertz. So we'll call it 30 megahertz. Typically, you want the roll-off to be above that, right? Because you don't want to start to attenuate your signal. So we're gonna select here 32 megahertz, 2 to 5 megahertz above the bandpass frequency is good. So we want 30. Let's go to 32. Okay, and if we wanted 32, maybe we go to 35. Okay, it's not that critical. I would say a minimum of 2 megahertz above. 2 to 5 megahertz is the rule of thumb. Okay, so now here's where we select the order of the filter. You can see there. So we're going to go with a 5th order filter. That's 5 components or 5 poles. And then here we have the input impedance. You can see there. We all know that the input and output impedance of our systems is 50 ohms. Okay, and then the bandpass ripple. Okay, so what this is basically how much ripple you would get in the bandpass. Okay, so you know the 10, 11, and 12 meter, you're going to get a slight amount of attenuation, and you can actually determine what that is. So I'm going to go 0.01. Okay, and you can see if I mouse over this, right, it's in dB. So 0.01 dB is not very much attenuation. Okay, so now these are our parameters that we use. It's pretty straightforward, and we'll go ahead and look at the schematic. Okay, so there's our schematic. You see on this side of the screen, on the left side, the termination is 50 ohms. On the right side, 50 ohms. And then if we count the number of lump components, we have 5. So that's our 5th order filter. We have an inductor on the input, inductor on the output. So let's go ahead and take a look at those values. Okay, 188 nanohenries. We'll just round these off. 130 picofarads, 392 nanohenries, and then again 130 picofarads, and it ends with 188 nanohenries. Okay, so the input and output inductors are the same. So that's a 5th order low pass filter for the 10, 11, and 12 meter bands. And if we go ahead and plot this, here's our roll off. Okay, so it's starting at 1 megahertz all the way to 100 megahertz. Okay, and here's the roll-off point. So what's nice about this software is you can just kind of mouse over here and click, and when you click, it shows you on the bottom of the screen what the frequency is. Okay, so right there, 35.6 megahertz. Okay, so right here is where it just begins to roll off. So we click on that, and we're getting about, where are we here? Click on it again. There we go. Get about 34, 35 megahertz where it begins to roll off. Okay, and then you get a nice sharp roll off, as you see, all the way to 100 megahertz. So let's talk a little bit about harmonics. Let's say we're at our harmonic frequencies. We're going to look at the 2nd harmonic, 3rd harmonic, 4th harmonic, etc. So what does that mean? If a fundamental frequency was 30 megahertz, which is the 10 meter band, just round it up slightly, we'll keep the math simple. Basically, the fundamental's 30. So the 2nd harmonic is 60 megahertz, the 3rd harmonic is 90 megahertz, the 4th harmonic is 120 megahertz, right? Usually, by the time you get to the 5th or 6th harmonic, okay, it's not a problem. It's going to be well below the fundamental frequency, and we'll look at that on the spectrum analyzer in part 2. So let's just take a look here, okay? We basically said the 2nd harmonic is 60 megahertz, which is here. And if we cross-reference, okay, we see we're getting about 23 dB of attenuation, which is very good. Okay, and if we get to, let's say, 90, which is here, okay, where I have the pointer, you can see that's 90 megahertz. That would be the third harmonic, and we're getting somewhere between 38 and 46. I'll put it right in the middle there at about 42 or so, 42 dB of attenuation. So this filter would perform very well, and again, it's very easy to design. If we go back to the design tab, there's only a few parameters that I need to select. Okay, the topology, which would be an inductor on the input and output. Okay, and then the family. Okay, and I'm using Chevy Chez because that roll-off is much sharper. Okay, and then we need to know the frequency. Okay, we can use a fifth order. What happens if we go with a seventh order? Just an example. Okay, we're going to go ahead and click seventh order. So now we'll have 7 poles or 7 components. There you can see it. Okay, if I pan back here, you can see the whole thing. And of course, the component values will change. But let's take a look at the plot. And we see the plot is much sharper, right? Okay, now here we're getting a 46 dB of attenuation, not at 90 megahertz, but at 60 megahertz. So this has a much sharper roll-off, but probably not necessary. Like I said, we're going to build this and then test it and see where we're at, see where the second and third harmonics end up to be. We want to be at least 40 dB down from the fundamental. That's the FCC requirement. So we don't want to over design and add more components than we have to. So let's go back to the design tab here, and we'll go ahead and change that back just to do a quick comparison. And there's the roll off, not quite as steep, as sharp. Okay, so again, this is a great design tool. Very fast to design a filter and then go ahead and build a filter and test a filter. So that's basically the overview. And I thank you for your time. RF Man.